we did actually get into this somewhat last week towards the end. We started briefly going over end behavior. So somebody tell me what you remember about end behavior. What does end behavior mean? When you study the end behavior of a function? Yeah, what you're able to do. And end behavior is determined by the lead term. When you're given a function in standard form, all you need to do is look at the lead term. Specifically, you look at the coefficient and you look to see if it's positive or negative, the lead coefficient, and then you look at the degree and differentiate between even or odd. And yeah, I'll do that first. I'll usually check the degree first. And then what we did go over is this type of verbiage: up and up, down and up, down and down, up and down, which in each case, like that phrasing, what's kind of understood is that the first word you say means what the left arrow is doing, the second word tells you what the right arrow is doing. But wait, how am I supposed to memorize that? Well, you could memorize the grid. There's only 4 types of behavior to memorize. Or the way I learn it is I associate it, I relate it to something that I already know. What type of even degree polynomial are we familiar with already? What? Quadratic, right? Yeah, a parabola. And as far as this is all about the arrows. As far as the arrows go, there's only 2 possible ways the arrows can look at a parabola. I'm sorry? Well, either they both go up, or they both go down. So what this is telling you, what this graphic is telling you is, even if it's not a parabola, if it's 4th degree, 6th degree, 8th degree, the only thing that's going to change, the only thing that's going to look different if it's a 4th degree polynomial, a 6th, an 8th, 10th, is that in between the arrows, you might get a whole bunch of this in between. But at the end, the arrows have to either both be up or, both be down if you have an even degree. Your degree is even. As far as an odd degree polynomial goes, what's the odd degree polynomial that we're most familiar with? A linear line. What determines the direction of a line? The slope. Coincidentally, when you look at it, slope-intercept form, where do you find the slope? The slope is the lead coefficient. It's the number in front of the x. Okay? And if that number was positive, the slope would go this way, which means that the left arrow would be down, the right arrow would be up. If the slope was negative, it would go this way with the left arrow up and the right arrow down. So what this graphic is telling you is that even though if it's not linear, as long as it's odd, 3rd degree, 5th degree, 7th degree, 9th degree, in between the arrows, you might get a whole bunch of this stuff. It might turn a lot, but the arrows themselves have to behave the same way. Now, end behavior can be expressed using the phrases that I gave you, but it's also very possible that they might express it in arrow notation, which, believe it or not, should not be completely foreign to you. You saw arrow notation in Algebra 1 when we did asymptotes, exponential functions, and you had that like invisible line that the graph got close to, but never actually reached. You have seen arrow notation, but let's go over it again. Arrow notation just gives you directions. The same way here I'm writing left and up and right and down. It's just a translating English to Spanish, but it's telling you the same thing. It's giving you directions. When I say x approaches infinity, what direction are you headed when the x-axis is approaching infinity? So the x-axis goes up. When the x-axis approaches positive infinity, what direction are you headed? To the right. This is a different way of saying. I think I only got two.
Oh, nice.
Oh, wait, Starburst.
Yeah.
That's not gonna get caught in your braces?
No.
Liar.
Thank you.
Well, so this is saying that the right arrow, well, f of x, what variable means, yeah, what variable means the same thing as f of x? The y. And when y goes to positive infinity, what direction are you headed? Up. So in up and up n behavior, the right arrow is headed up. When x goes to negative infinity, what direction are you going? Left. So the left arrow, if you look at the y, is also going up. When you see x going to positive infinity, it's talking about the right arrow. When you see x going to negative infinity, it's talking about the left arrow. When you see f of x going to positive infinity, it's telling you that that specific arrow is going up. When you see f of x going to negative infinity, it's talking about that specific arrow is going down. That's arrow notation. We'll write it a few times also. Here are some just various examples of different types of n behavior. In red, you see the function that you're probably most familiar with. I drew two parabolas. I also drew two lines. In blue, I drew other types of functions that exhibit the same end behavior, but the only difference is that they turn in between. They get all curvy, squirmy. But the end behavior is the same. Both of these are up and up end behavior. Both of these are down and down end behavior. We'll also write in arrow notation. Both of these have left arrow down, right arrow up. Both of these have left arrow up, right arrow down. How you doing today? Get some sleep? So let's determine the end behavior. First thing we want to do is identify the lead term. What is the lead term in this first function up here? 4x to the third, the lead term. I like to look at degree first, just in my mind that organizes things better, and then lead coefficient, but it doesn't really matter. What type of degree function is this? What type? It is good. It's odd. And is the lead coefficient here positive or negative? It is positive. So in my mind now, I go in my time machine back to the odd function I was most familiar with, which are lines. And when a line has a positive slope, what's the left arrow doing? The left arrow, definitely can't go right. Where's the left arrow going? The left arrow will be going down. And where would the right arrow be going? On a positive slope. Up. So down arrow and behavior. But wait, there's more. Let's also, just for fun, let's write this in arrow notation. So in arrow notation, I would say, the way I would say my left arrow would be that x is approaching negative infinity. The way I would say my right arrow is that x is approaching positive infinity. And now let's see what the y is doing. So f approaches, f of x approaches. So if my left arrow is supposed to be going down, what would I put next to the f of x? Negative infinity. If my right arrow is supposed to be going up, what would I put next to f of x? Yeah, up means positive infinity. It's arrow notation. Here's another one. First, let's identify the lead term. This isn't simplest form, it's not in standard form, so be careful. What is my lead term here? negative 2x to the fourth. I would tell you to look at the degree first, then you could figure out what type of function to relate it to, and then look at the coefficient, but it doesn't really matter. What type of degree is this? Even degree similar to a parabola, and my lead coefficient is negative. So what are the arrows going to do here? Because it's even, if I'm going in the same direction, these will both be going down, like an upside down facing parabola. This is exhibiting down and down that behavior. Let's write this in arrow notation. As x approaches negative infinity, what's happening? And as x approaches positive infinity, what's happening? In this case, since both arrows are supposed to be pointing down, what am I going to put next to both f of x's? Negative. Okay, last one like this on this page. What's my lead term here? And even though it's not in standard form, the term that's going to determine my end behavior, the biggest exponent is the negative 4x to the ninth. Let's talk about the type of degree and the type of lead coefficient. What's the type of degree here? It is odd, kind of like a line would be. And what's my lead coefficient?
Negative.
Negative. So what's my end behavior here? Up and down, left arrow going up, right arrow going down, but let's also write this in arrow notation. So the way of saying my left arrow is to say x is going to negative. Like you're always going to have an x going to negative infinity. You're always going to have an x going to positive infinity, because that's your way of saying left and right. I want to know what the left arrow is doing. I want to know what the right arrow is doing. Then the one, so these are like independent. But then the dependency is then what's the y going to do? And if my left arrow is supposed to be going up, what's f of x going to do? Positive infinity. And if my right arrow is supposed to be going down, what's my f of x doing there?
Negative infinity.
Fax machine. Zeke, you got that? Yes. All right, these next few, I'll do this, we'll do this warm-up one thing together, but then after that, we're gonna start drawing sketches. Like, basically, like, I'll do this page for you, but then the next few pages, you're gonna do on your own, and then I'm gonna, we're gonna just check them afterwards. So, what do we know about the leading coefficient and degree of the function represented in this graph? Well, leading coefficient and degree, are what determine end behavior. So I can just look at the arrows. What type of end behavior is this graph exhibiting?
Down.
Down and up. Left arrow down. You always go from left to right. Right arrow up. And because it's exhibiting this end behavior, what's the degree? It's going to be an odd degree. And what's the lead coefficient?
Positive.
Okay, and then now this next one is what the next few are going to mostly look like. We're now we're going to infuse what we did last week with zeros and multiplicity. Notice this word, you're going to see this word a lot. What does that word imply? That there's a limit to the amount of precision you can have. It's just not going to be as exact as like a line would be. Like every point doesn't have to be perfect, but there are certain key characteristics that do have to be accurate. I would first graph my zeros. So here I have a 0 and -3. Here's what 1, and then that's 4. Remember, zeros mean x-intercept. Somebody asked me the question last period. It was actually not a bad question, right? Because the next thing I do is put the arrows. And she was really confused about where to put the arrows. And like as far as where the arrows go, yeah, maybe that's not super precise. But one thing I have to know is the arrows have to be on the outside. So like if I have my x-intercepts there, I'm not going to put my arrows in here. That wouldn't make sense. Like the arrows are going to have to be outside of the x-intercepts. And then the other thing that's important is where they face. So if I have, what type of degree is this? Odd with a negative lead. What are my arrows going to do? Yeah, left arrow up, right arrow down. I mean, as long as you put them outside of your zeros, you know, where they specifically go, that's, it's kind of left open to interpretation. It doesn't have to be perfect. The only thing left to do now, like we know that we're going to pass through, or that we're going to touch, like this graph has to touch all those zeros, but we have to factor in the multiplicity to see how to touch it. So let's just go from left to right and start off on this roller coaster. I'm headed towards this first 0. What's going to happen at that 0, -3? It's going to bounce because it was an even multiplicity, so it bounces off. Okay, so now I'm headed up. I'm going to have to eventually turn somewhere because I have to get back down to that 1. But once I do turn and go back to the other, it doesn't matter where you turn. The only way that you can find there's 2 ways you can find the location of a turning point. One will be a graphing calculator. The other one will be calculus. Of the 2, I think we're more likely to use a graphing calculator, but even then, what I've been told with the type of assessments, I do not going to force you to have a graphing calculator. So assume that if you need to know the location of turning point, it's going to be given to you. But we'll worry about that when the time gets there. So we're starting to turn around. What's going to happen when we get close to that 1? It's going to go straight through. And then eventually we have to turn in order to be able to get back to that 4. Okay, well, like what a turning point is like this, like when you're going up and then going down, or when you're going down and going up. Those are turning points. If your graph starts to like kind of like get a little flatter, that's not a turning point. A turning point is going up to down or down to up. Oh, you know what? I gotta skip that part. I'll have to go back to that. So when I go back up to the 4, what's going to happen at the 4? It's going to bounce. Why is it going to bounce off of it? Even multiplicity. So your graph doesn't have to look exactly like this, but the only real way that it will look different than mine is how high maybe you decided to take the turning point. Other than that, it should look roughly the same. Before we like, and look, this next part you're probably not even gonna need. This is more if it's free information Mondays. So you can say you learned something. Like before we get to these examples, let's go back to this first page because I skipped. Let's talk a little bit about turning points. You'll see this a little bit more tomorrow and on Wednesday. But turning points are also referred to as relative max-min, or what's called a local max or min. Have you seen any of those phrases? Relative max-min, local max-min, they're talking about a turning point. You can predict roughly how many turning points a function should have based on the degree. Now, the degree also told you something else that we learned last week. What did we learn that the degree of a polynomial tells us last week?
Last week.
Last week. Yeah.
The amount of zeros.
Very good. The amount of complex zeros, the fundamental theorem of algebra says that whatever the degree is, that degree is going to match how many complex, or it includes imaginary and it includes repeated, but it'll tell you how many x-intercepts. Okay. The degree can also tell you potentially how many turning points. But it isn't, see, when it comes to zeros, the degree is exactly the same as the amount of complex zeros. When it comes to turning points, the most amount of turning points you can have is one less than a degree. So if I have a 10th degree polynomial function, what's the most amount of times that a 10th degree can turn? 9, one less. But it could also turn, it could turn less than that. And you would go down in increments. Basically, right, so I just give you an example of 10, right? And you told me that 10 could turn as much as 9 times. Is 9 an even or an odd number? You would give me every other odd number below it. So a 10th degree function can also possibly turn 7 times. It could turn 5 times. It could turn 3 times. It could even turn 4 and still be 10th degree. 9 and every odd number below it. If I were to ask you, hey, how many times could a 7th degree function turn? 6 would be the maximum, but how many times could it also turn? 4, because now 6 is an even number, so 4, 2, and for the purposes of turning points, we even consider 0 to be an even number. So I don't think that's going to come up, but hey, at least I showed you something. Here, describe this type of behavior. See if you can do that on your own paper. Having some migration. Take you maybe like 15 seconds. The step is already done. Step, what type of behavior is it? What type of done? Alexis, what type of behavior is it? Very good. Left arrow is down, right arrow is up. And this is clearly when looking at the picture, down and up on behavior. And if we have down and up on behavior, that means that your lead coefficient should be positive and your degree should be odd. Okay. But then also, just for extra practice, and because we don't know how the questions are going to be worded, let's also describe the same end behavior that we just did in arrow notation. As x approaches negative infinity, tell me what happens. As x approaches positive infinity, tell me what's happening. Well, if x is going to negative infinity, that's the left arrow. What's the left arrow doing? It's moving down, so f of x would have to be negative infinity. And then how about the right arrow? Okay, so the same way that I did a sketch for you here, where it said draw a rough sketch, try to do the next 1, 2, 3, 4 slides. Is that the entire next page? Yeah. Do the entire next page on yours. See if you can draw those rough sketches. I'll give you maybe like 4 minutes, 3 minutes, 4 minutes, something like that. I'll give you till 8:55. Alrighty, Caroline. First, you want to. Last minute. Alright, here we go. Let's get started. The first one, the zeros are through -3, 1, and 3. I will start off putting that. And then, so I want my arrows to go outside of that with a degree of 3 and a leading coefficient that's positive. My end behavior should be down and up. So my left arrow is going to be down here somewhere, right arrow up here somewhere. But now I got to look at the multiplicities. Oh, and I put an extra one, didn't I? It's not in this one. Sorry, I misread it. I saw that 3 that's thrown in. Okay, everybody agree so far?
Yes.
All right, so with at -3 with a multiplicity of 1, what's going to happen? I'm going to go straight through. Okay, now when I go straight through it, the only way I can come back down to that 1 is I got to turn around somewhere. Where you turn around really isn't important because it's one of the limitations to our precision. But when we do come back down into set negative 1, what's going to happen? We're going to bounce because it has an even multiplicity. We'll bounce off of it. Keeping in mind this is A. I did it backwards?
No.
Oh,
Okay. Still gonna leave the same. Thank you. Sorry about that. That one was James. Questions there? Good. All right, let's go to the next one. This one has zeros at 2 and negative 2. With an even degree and a negative lead coefficient, you should have identified your end behavior as being down and down. So I just put my arrows outside of those points. And both multiplicities are even. So when I go up and touch them, I have to bounce right off. But I'm headed down now. The only way I can get back to that 2 is to come back up. But when I hit that, I gotta bounce down again. Should get you thinking of McDonald's. Questions there? See it? Split ends. Okay, this one has zeros at 1 and at 3. The degree is odd with a negative, so it's activity up and down and behavior. So I need this arrow facing up, this arrow facing down. The first 0 at 1 has a multiplicity of 1, so what's going to happen as I get close to that? I'm going to go right through, but then eventually I got to turn around. But when I turn around, since I have a multiplicity of 2, it pasa. It bouncy. Questions? And then, that's what you would have done. Now we have 3 zeros, negative 3, 1, and 4. And we have its 5th degree. Okay? With the negative, what's the end behavior there? Up, left arrow up, and then right arrow down. Up, down. On the first cell, we're at negative 3 with a multiplicity of 2. What's going to happen? Yeah, we're going to bounce. Then we got to come up. How high we come up, that's up to you. Alright, now we're going to go straight through. Then we're going to bounce, bounce, and then. The only real variation you should have on your graph is, again, how high this goes up and how low that goes, but that can vary because it's a sketch and we don't. If you paid attention to it, you're going to deliver this thing up, but if you were listening to this, what did I tell you you would need in order to be able to find the exact location of the turning point? Graphing calculator or calculus, yeah. The ability to just calculate what's called a derivative. Which obviously we won't have. Alright, these next two are going to be a little bit different, whereas you're not being given the zeros, so we're going to have to find them ourselves. One of them is fair, which is this one here, the other one is not, but we'll deal with it. Point is, we still want to sketch a graph. Okay. Now, what we can tell by looking at this in standard form is the end behavior. What's the end behavior going to be? With a negative lead and an odd. Yeah, we're going to have up and down end behavior. Left arrow up, right arrow down. But unlike the previous ones, we don't know the zeros, we don't know the multiplicities. The problem is that in order to find, what are some other words for zeros? Yeah, solutions would be the big one, specifically solutions when y is 0. The thing is, when anything that's not anything that's more than quadratic, this is not quadratic. The only thing you know how to do is factor, and there's other methods other than factoring that you haven't been taught. So this one is fair. This one can actually be done by factoring. The next one that we're going to do can't. So let's give you the 0 in the next one. How can this be factored? There's a greatest common factor of x. And see, the thing is, you're normally usually using zero product property when all the factors are linear. But as long as the factors are at least quadratic, like we know how to solve quadratic equations too, so I can just use zero product property now. This x can be 0. What would the multiplicity be? 1. It doesn't have an exponent other than 1, so just 1. And since this is already quad, like I can't factor this anymore, but I can say that 3 minus x squared is equal to 0, and then just solve that. Minus 3 minus 3, negative x squared is equal to negative 3, multiplied by negative 1 to cancel out the negative. What's x going to end up being? Plus or minus is good. Plus or minus what? Square root of 3. Plus or minus square root of 3. And each of those have a multiplicity of 1 also. Positive square root of 3 is not the same thing as negative square root of 3. Oh wait, how am I supposed to know where to find that on the x-axis? Well, you can use a calculator, or you can use your mental math. Since you know that 3, as far as perfect squares go, 3 is in between 1 and 4. Square root of 1 is 1, square root of 4 is 2. So you know it's going to be in between 1 and 2. And since 3 is closer to 4, that means it'll be closer to the 2. So it will be closer here to positive 2. Here it will be closer to negative 2. And again, in between the 1 and the 2. And then I also have a 0 here. Oh, sorry. We said the end behavior was going to be up and down. So left arrow up, right arrow down. And since they all have a multiplicity of 1, we're just going straight through. What's the only thing extra that we had to do here compared to the last 4 that you guys did on your own? Find the x-intercept. That's the only thing that we did there. And I would guess that on the quiz on Friday, you probably won't even do that. Maybe on one of them. So this next one is the one that's kind of unfair because, again, the only way you know how to solve is by factoring. This can't be factored. I'm just going to give you the 0, 0. Don't think I didn't do this in my head. I used the graphing calculator just to get the zeros quickly. You're going to have one at approximately negative 0.41. You're going to have one at exactly at 1. And we're going to have another one approximately at 2.41. The multiplicity of this one is 1. The multiplicity of this one is 2. The multiplicity of this one is 1. But wait, I don't get it. How'd you get it? I just told you. I had to do a graphing calculator. I don't think that you have to know how to find that. Because that expression can't be factored. That problem can't be factored. But what you are expected to know how to do, now that you have this information, combined with what we learned today, what's the end behavior going to be here? It is very good. Very good. Because this is negative and even, it's going to be down and down. That should be enough for you to graph it on your own. At least a sketch. Negative 0.41 is between 0 and negative 1. 1 is here. 2.41 is in between 2 and 3 somewhere. Just a sketch. Down and down means they're both facing down. And The ones that have a multiplicity of 1 go straight through. The one that has a multiplicity of 2 bounces, and it also looks like an M. And then you guys did practice this weekend? Oh, that's right. You went to that Thursday. How was that? This one, this is the last one that I did last year, yesterday, right? So this will be the last one for you guys. So we'll wrap it up over everything. Wait, whoa, but this is crazy here. What's different about this one and the other one before? Meanings? Yes, this one does have parentheses, meaning.
Meaning to try to get it.
What form is this polynomial in? It starts with F and ends with active. Yeah, this is backward form. So out of the two main components that we've been looking at, which are the zeros of a function and the end behavior, which one can you just like on the last two that I just did, we're gonna have to acquire everything on our own. We're not being told the end behavior, like we're not being given specifically the degree of loss, that we're gonna have to get everything ourselves. Of the two, which one should be the easier one when you're in backward form? Probably the zero, sure. Okay, but let's start with that. What are my zeros going to be here? Well, the first one here is going to be on x is 0. What's the multiplicity? This we did last week. What's the multiplicity there? This is not new. Last week you were given backward form and asked to find the zeros. What's my next zero? What's the multiplicity there? 1, because that parenthesis on the outside, you can't see the exponent. And then what's my last zero? And what's the multiplicity there? 5. Now what we're missing though is the end behavior. End behavior, we need the least term. Got it, thank you. We need the lead coefficient and we need the degree. Well, we actually do know how to find the degree in factor form. Just requires adding. What's the degree of this polynomial going to be? 10. Yeah, you just add up all the exponents of each of the factors. 4 plus 1 plus 5 is 10. So this is the 10th degree polynomial. And the lead coefficient, think about it, when you factor, you're multiplying, right? This first x is negative, this x is positive, this x is positive. What is negative times positive is positive? It's negative. So with an even degree and a lead coefficient that's negative, what should the end behavior be? Down and down. It's going to be down and down. So now let's sketch. 0, 6, and -7 with both arrows facing down. The first -7, what's going to happen? It's going to get, no, it's definitely not going to bounce. It's going to get close, it's going to flatten out a little bit, and then it's going to go through. It's odd, but it's greater than 1. Okay, then eventually we got to turn around and come back to 0. What's going to happen at the 0? That one's going to bounce because the multiplicity is even. And then we come up, and then what's going to happen at the 6? Now, I made some mistakes. I forgot to erase some of the previous handwriting, so this one already should have something kind of like it on there. Some of the factors would be like that, but any questions for me?